My name is Krassimir Tzvetanov, and I am a graduate student at Purdue University, and I also am a research assistant at the CyberTap program, which provides technology assistance to businesses around the state of Indiana. You can get in touch with me if you email me at one of those two emails, and if you need more information about me, this is my LinkedIn profile. Okay, so let's see if we can make this a little bit more interactive, despite the fact that we are dealing with online and online presentation and Discord. So if you have any questions, please send them in the Discord channel for the track, and I will try to incorporate the answers as I go. So I hope that this is coming through clear. Okay, so this is also a class that I normally teach over a couple of days. So here I have taken excerpts from some of the kind of highlights. We'll cover a couple of attacks, how they work, actually more than a couple, but then we're going to also look at how to mitigate on system level using external providers and so on. And also we'll look at some of the motivation for attackers and how, why they organize those attacks and what capabilities they have. Again, if you have any questions, please send them in the Discord chat. Okay, cool. So what is a denial of service? That's kind of a question I want to ask you. Just want to see the level of engagement and also what people have as a concept for this. Okay. I apologize 1 second because I'm having a Discord problem. Okay, I guess no feedback there. Okay, so anyway, so denial of service is basically a resource exhaustion, which as a result leads to a lack of availability. There's a common misconception that denial of service is a lot of traffic over a pipe. And yes, this is partially true, but denial of service does not need to be represented as a lot of traffic over a pipe. As a matter of fact, some of the really good attacks would result in very little amount of traffic on the pipe, and it would be very difficult to detect those just using monitoring of SNMP counters on the interfaces. Now, another thing also to consider is resource exhaustion leading to lack of availability. Now, how is that different from a website being overloaded? So things look very similar in many cases in the way that they manifest to the end user. So keep that in mind, because the way we deal with overloaded websites is also a potential way we can deal with denial of service attacks, just adding more capacity in a smart way by figuring out where the bottlenecks are, just the way you would optimize a website to be able to deal with more traffic. Okay, so from security point of view, from operations point of view, and from business point of view, denial of service looks slightly differently. And this is somewhat important because we have different players here. One of them is the security team, which usually is a small player in that space. Then the bigger player would actually be the business. But from security point of view, if we look at the CAA triad, we have confidentiality, integrity, and availability. So this is affecting the availability component. Many people in the security field focus on confidentiality and some on integrity, but availability is usually ignored. So again, DDoS is a security event which usually disturbs the availability component. From operations point of view, so those will be the network administrators, system administrators. From their point of view, this is going to be just an outage. And why is that interesting? Well, because those people know how to deal with outages. Most of the people that operate large networks have certain level of redundancy. So there are good ways to leverage your redundancy, balance traffic in order to be able to accommodate larger attacks. From business point of view, it's a matter of financial losses. And why is that important? Well, if you want to procure equipment or additional bandwidth or personnel to help your company deal with denial of service attacks, you need to be able to demonstrate value. And the business people will be looking at those money that they have to spend as an offset of losses that they will incur. So if you know that your website will suffer $10 million loss over a 24-hour period if it is down, then you can very easily make a case that there's certain probability of you being attacked, and to your current bandwidth maybe, or current posture will allow you to withstand attacks below certain level, but then if it is above certain level, you will be offline. So you can say, well, we'll be losing $10 million a day, and the probability is X. That means that maybe you can ask for 10, 20% or whatever it is in terms of investment for mitigation. You can also think of it as an insurance policy. You basically, or the way you buy an insurance policy, you pay certain premium, and it helps you in the event of particular type of loss. Any questions so far? Okay, so just quick disambiguation between terms, denial of service versus distributed denial of service. I think to most people this is pretty obvious. So in the case of denial of service attack, we usually have one source of the attack that sends traffic to the target. In the case of distributed denial of service attack, we used to see usually botnets employed to do that. So the attacker would issue a command to the command and control server, and then the command and control server would talk to a botnet, which would execute the attack or deliver the attack traffic. So here, basically, you can see that the difference between denial of service and distributed denial of service is that you have multiple sources of traffic. Now, things became a little bit confusing about 5 years ago when reflection became very popular. Actually, now that I think about it, it's 6-7 years now. So with the reflectors, we don't have a command and control server. We don't have a botnet. We have a bunch of reflectors, and those reflectors will be the parties that are going to be delivering the attack traffic to the target. And how this works, we're going to see in a few minutes when we look at the reflective attacks. So anyway, just bottom line, the denial service attacks, usually you have one target, one attack traffic generator. With distributed denial service attacks, you have multiple generators. Now, this also should not be confused with somebody spoofing IP addresses during the attack when there's only one attacker and they're spoofing the IP address within the packet. And then on the receiving end, it looks like it's multiple IP addresses. That would not be DDoS. Okay, so first, looking at volume factors, why is DDoS growing? Why do we get blog posts with bigger and bigger numbers, how this company or that other company mitigated bigger and bigger attack? And does that really matter? Is that really relevant? Well, let's look at this. First factor would be overall bandwidth. So the internet is growing, and the individual links are doubling in size approximately every 2 years. It's a little bit delayed. It's not exactly Moore's law here. But if today I have the ability to execute an attack that will be 20 gigabits, or let's say 30 gigabits, but I can only transfer 20 gigabits out of this attack, that means that the medium is limiting me to this amount of attack traffic. 2 years later, I will probably be able to easily transport out of the same location that I'll be generating the traffic, 40 gigabits. That means that I can deliver more attack traffic. So if we extrapolate this to the entire network, the network has more overall bandwidth and it can carry more attack traffic. Now, also, if you look at it from a different angle, the network itself is a filter. So if you have a botnet or generating surface that may be reflectors, for example, not bots, that are not well distributed around the internet, and for example are behind slow links, that may also impede the ability for attack traffic to be delivered to the target, no matter how much attack traffic is actually generated. Think about something that is, let's say if you have a large botnet behind the Great China Firewall and you want to attack something outside of the firewall, well, good luck. Overall bandwidth, one of the factors why we're seeing bigger and bigger attacks. The next factor is reflectors. We're going to cover this in a little bit more details. And then we have IoT embedded devices and so-called SOHO devices. We'll look in more details in those in a second. And the last few things are content management systems, the so-called booter or stressor services. And there's also a lot of available information on this topic nowadays. 20 years ago, it was very difficult to get a SIMFOD going because it was difficult to find the tools. And even if you found the tools, they would normally come with errors in them. So you had to know C fairly well to fix them and so on. Now, all information is fairly available. So even kids in high school can very easily set up capability, and this will kind of come into play into the booters and stressors. Now, one final thought here on this slide, the overall bandwidth, as I said. So if we had an attack that is 600 gigabits per second, and this was 6 years ago, that would have been quite a bit of a thing, but now 600 gig is not that bad. And again, this is because there's more overall bandwidth. So this is what I was saying, is that the absolute number of the attack doesn't matter that much, just because those numbers are going to be growing increasingly, just because the available bandwidth is growing. Okay, so home routers, IoT devices, the major problem there is that those are very easy to compromise. They have a lot of bugs, a lot of issues, and as a result, just people abuse them, and they can build fairly large botnets. A very good example would be the Mirai botnet, which was very popular at the end of 2016. The FBI did a fairly good operation, took down the folks that started the botnet, but one of them released the source code under the moniker Anna Senpai. And this was actually because they were trying to kind of have a plausible deniability. Why do they have the source code? Well, because they downloaded it. So if they make it open source, that's great. If they get busted, then they were like, oh, I downloaded the source code, that's why I have it. However, this caused quite a lot of havoc, because a lot of other players downloaded the source code, started modifying it, and now we have a bunch of Mirai variants that they used. So now, major events, another major event was the lizard stressor attacks around Christmas of 2015, which was again embedded devices. Compromised CMS systems, mostly Joomla and WordPress are targeted. A lot of that started around 2013 with the attacks against US financial institutions after the some of the penalties that were imposed against Iran. And this is still continuing to be a trend, but it is not that that big as, for example, IoT devices. Here, the major problem is that again, there are a lot of bugs in those systems. People install them once and they never upgrade them. So this becomes a very easy target of exploitation. Now, one other thing to note is that as attackers are becoming more and more advanced, there was a time when we would see a PHP bug, and then there would be a lot of scanning because people are trying to figure out where this bug can actually be exploited. Now they preemptively scan at very low speed, but they record the versions of different instances of WordPress and Joomla. And when a bug comes, they just query their database, and now they know what to hit. They don't have to do additional scanning. I apologize. Okay, so booters and stressors. Well, it's the same thing, just two different terms. Those are usually used in computer by people that play computer games, and they use those services in order to boot somebody out of the game, or at least decrease their performance, so that they can steal their gold or whatever they need to do to disable the player temporarily. So those, started around World of Warcraft, then League of Legends, and so on. Those are fairly inexpensive. They produce usually small attacks, 5 to 10 gigs, up to 40 gigs is exceptions, is what I have seen. And usually the duration is short for a couple of reasons. First, to boot somebody off a game or at least disrupt them significantly only takes about 3 to 5 minutes, maybe a little bit more. But also when the attacks are smaller, it's harder to have those tracked and also detected even. Many of the providers still are using MRTG graphs or derivatives that only scan every 5 minutes. So when they keep the attack short, they also avoid detection. Okay, low cost resulting from reflection. So let's look at this. If we have an attacker that operates a botnet, they have to have multiple components come into play. So they have to support a command and control server. They have to have all those bots, and they also have to have the software running on all of those, which means that they have to infect those machines. Now, if they were to basically do that, they would have to have, let's say, a mail list where they send particular email that entices people to click on a link or something along those lines. That they also have to operate the software that's going to be infecting those machines, and so on. They can also alternatively go and buy those infections. About a couple of years ago, when I did some research, the pay-per-install rate for home computers was about $140 for 1,000 machines in the US. So it's not that bad, but still that's an expense that they have to incur. Also from a legal point of view, there's a couple of things that are happening here. So each of those machines that is compromised is actually unauthorized access to a computer. And then also all the traffic is going to a particular command and control server. So it is much easier for those people to be traced back and then investigated. And then this machine can also be seized. The database can be investigated, and so on. So there's a lot of traces that they're living here. So it's not only the monetary cost, but also there's a lot of legal cost that incurs or legal risk. Now, if they were to use reflectors, the attacker just needs to get a list of reflectors, and then all they need to do is send the traffic to those misconfigured machines, and then they're going to bounce the traffic back. So here they are exploiting those machines. However, they are not compromising any of those machines. Until about probably 9-12 months ago, this was also fairly difficult to prosecute. Now, the Los Angeles office of the FBI started using fraud by wire. This is one of the ways to do this, and they have been successful in prosecution. But until about 9 months or a year, this was also difficult to prosecute. So, any questions? Okay, I don't see any. Okay, cool. I am hoping I am looking at the right channel on Discord. I'm just making sure that I'm in the right place. Maybe not. Okay. Cool. Then we'll continue. So adversary, just quickly here, it could be a lot of different things. It could be professional DDoS operators, just booters, stressors. Hacktivists was popular a while back. I foresee around the current events, maybe there'll be some hacktivism showing up soon as well. Motivation, fairly straightforward here. Could be just trying to make a statement, or could be financial gain. About 3-4 years ago, there was a lot of emails going to people stating, hey, we're going to deny service your website if you do not pay X amount of Bitcoins. Now, in the beginning, that sounded scary because a few of those actually followed up with attacks, but for the most part, turned out that those were mostly bogus. and they were just using people's fear. But again, extortion is a possibility here, and other kinds of financial gain can be envisioned as well. Also, like destroying the branding for a company is, you know, one thing that can be used. Just targeting company, and like the company may be afraid that they will lose their brand. So, for example, if Nike is threatened that their website is not going to be available, or major media, for example, is threatened, they may submit to that or figure out how to solve the problem. Anyway, another thing that's interesting here is that many providers that operate web application firewalls, they have fairly heavy set of rules, and during attack, to alleviate the pressure on the compute component of their firewall, they may disable some of the more complicated rules. And this has been used in the past to attack somebody so that they remove some of the more advanced rules in their rule set, and then the attacker continues with exploitation of the website. Okay, what are the booters? We kind of covered a lot of those in the overview slides. Fairly expensive short bursty attacks, rudimentary scripts, and so on. Now, looking at the user interface, this is how those look. You just basically go to a website, and you can pay, you know, $15 a month, for example, for basic service, 200 and something, and so on. You can see the different prices here. Some of them also come in Bitcoin, PayPal, and all kinds of forms of payment. They also offer dashboards like this one, where they give you just general information about the site, how many attacks are executing, and so on. What's also interesting to note is that it appears that those frameworks are fairly commonly reused. You can just see that the template here is different, so the colors are different, but it's the same software behind it. There were also cases where the same operator would run multiple front ends, knowing that their service is not very good quality. So people go buy service from one of the front ends, then they get upset that the service is not working very well, then go buy service from one of the other front ends, and they think they're buying from different operators when they're buying from the same fraudster. So that's kind of on that topic. Questions? Okay, so we're going to look at a few attacks in particular. One of them is SymFlood. This is a classic attack which has been working for I don't know how many years. It was probably 25 years ago, the first time when I encountered it. And it is still relevant, unfortunately. What does this attack do? Well, it exploits the three-way handshake. What happens during the three-way handshake? We have a client that sends a packet with the SYM flag on, and then the server will respond, and they will set the acknowledgement flag on, and then this is going to establish the connection in one direction. Now, in order to establish the connection in the other direction, we'll have to have one more acknowledgement packet sent from the client to the server, and those three packets are known as three-way handshake. One thing I forgot to mention here is see how this server has to keep state for all of those incoming packets. I'll quickly go back here. See how the first packet comes in, and the server has to keep state here. I only have displayed the sequence number, but there's other information that the server has to keep as well. So what is this attack doing? Well, it is exploiting this very need of the server to keep state of all incoming SYM packets. Once we have too many packets, there will be not enough slots here to store information about those. And even though the server is responding, if the attacker changes the source IP address to random IP addresses, there will be no pattern that can be filtered by the defenders. But then all those packets will be going to random places on the internet. Those machines there will be dropping those addresses or those packets, or responding with some form of ICMP, depending on if there's a firewall configured and so on. But they will not complete the three-way handshake, which is going to make this server wait for 60 seconds before it can reuse this slot. Well, having in mind that those slots count between 1,000 to 4,000, okay, 1,000 and 4,000, they will, you know, 1 packet per second. You can easily see that here we're talking about bandwidth on the order of qubits per second that can saturate completely a server. So that's fairly low bandwidth that would require for this server or server farm to be saturated. There's also different ways the queues are organized. I'm not going to a lot of details here, but the idea basically is that in some cases you may also have even smaller queue length. So how do we solve this problem? Actually, let's look at the math first. So we have the back, let's assume 1,000 slots in the queue. The backlog timeout or SYN receive timeout is 60 seconds. The SYN packet is, you know, the minimum packet that can be transmitted is basically 64 bytes because that's the minimum frame that can go on Ethernet. The minimum legal frame, then you have inter-packet gap, which is another 20 bytes. So let's say 84 bytes. Well, what does that mean? That for 1,000 packets per minute, we will be looking at 1.4K in order to saturate this machine. And as I already showed in the previous slide, some machines may be configured with even lower number of slots. Now, if we decide to lower this timeout here from 60 seconds to 30 seconds, then this number will merely double, 2.8 qubits. Oh, who cares? Well, let's decrease this number 60 times. This thing is going to go up 60 times, which we're still going to look at like 90 qubits per second, which is again nothing. However, when we start going to a second or sub-second, now the round trip time for some coins that are far away will not be sufficient for that to complete the two-way handshake. Thus, this really doesn't work because we will not be able to have everybody complete two-way handshake. Just thinking about a satellite uplink, if it goes to one hop, we're looking already at 500 to 600 milliseconds latency. Just fiber, you know, going around, you know, from one continent to another, we're looking at 200 milliseconds, 300 milliseconds. So this is not a good way to mitigate this. Increasing the number of slots is another way to deal with that. But again, increasing the slots just double, like by 2, will just double this. We require 2 times bigger number. Again, this doesn't scale very well. This is how this will look if we use NetStat to observe the state of the server on the receiving end. You're going to see a lot of packets, sorry, a lot of sockets in SYN receive state. And that's basically very kind of very obvious way to detect this attack. It has a very clear fingerprint. Now, how are we going to mitigate this? Well, we're going to use something called SYN cookie. So the SYN cookies are basically going to store this information. If you remember, there was this set of this storage that had many slots. That is the component that's exploited. Well, if we can find a way to preserve this information without keeping it in the memory of the server, then we will be in very good shape. So this is what the SYN cookie essentially is. It is going to preserve this initial sequence number by encoding it into into the return packet. So it's going to take some key options like source IP address, destination IP address, source port, destination port, and a subset of the options. And it is going to hash them and then encode them back into the sequence number of the packet that it sends back. So let's see how this thing will look. We have source IP address, TCP options, interval, and so on, and then calculating the SYN cookie. Let's call this SYN cookie is 345. Here I'm using intentionally small numbers because we're human and we don't work very well with numbers in the order of billions. So here this sequence number is embedded into the packet. And then when the third packet comes in, because the rules dictate this number will be increased by 1, And when it is received on this side, if sync cookies are enabled, because obviously they are, it will calculate the same hash, add 1 to it, and if the number matches this one, the server now knows for sure that the first packet actually arrived, and here the hash will match. Now, one thing I think I didn't mention is also there's a time interval there, time of arrival, which gives the 64 seconds resolution, which is pretty close to the 60 seconds timeout for the SYN receive slot, which is protecting us against replay attacks. So this is preventing somebody from replaying SYN cookies and packets, sending them back to the server, just because this timer would have the time of arrival would not match, so the hash will not match, or will not be within 64 seconds. So anyway, that's kind of how the SYN cookies work. Any questions? Okay. Okay, so now we're going to look at reflection and amplification attacks. This is when I was saying initially that this makes things a little bit more confusing in the distributed DNS service attacks, or made it confusing 5 years ago. Now it's pretty much common practice. It's actually the predominant type of attacks nowadays. But having said that, there are two terms that often get conflated, but they're different. One of them is amplification, the other one is reflection. So the reflection one basically is the ability to send packets and then force the other side to send the response to another party. Usually this is achieved by changing the source IP address, and many protocols would not do this validation. On protocol level, it will allow for the other party to receive something. Yes, the slides will be available. And actually, I will also point you to another link where I have a larger deck. So I'll do that at the end. Thank you for, or we'll post it in the program. Thank you for asking. So yes, as I was saying, with UDP, a lot of the protocols on top of that, like DNS, for example, they don't need to establish two-way handshake. So if you spoof the source IP address, it's very easy for this thing to contextually make sense for the servers and for them to return proper responses. Now, if you do this with protocols like TCP, at best you can have only the SYN ACK packet reflected somewhere, which still does give you some level of amplification, and we'll look at that in a second, but it is not as efficient as with UDP and protocols on top of that, like DNS, for example. So reflection illustrated here. We have an unwilling intermediary, which is the reflector. Here, the attacker sends a packet. They are going to spoof the source IP address with the IP address of the target, and then the response is going to hit the target. Okay, now protocols, as I mentioned already, the ones that are really easy: DNS, NTP, SSDP. Now, before we go to actual attacks, I want to show you amplification, just so that you know, I'm exhaustive in this. So amplification is when you have a small query. For example, DNS is a very good example. We have an any query that only asks for those 9 letters, basically, right? Technically 10 because there's a dot. This will be at best 64-byte packet because of the framing, as I discussed earlier. However, the answer is going to be much bigger. Now, note here that protocols like DNSSEC make things even worse, just because then the records here will have much more data. They'll have public keys and so on and so on and so on. So this answer here will be much bigger. Now, many years ago, DNS could only respond with up to 512 bytes, just because this was the specification. But then with eDNS 0, we currently have the ability to send multiple K traffic back. Okay, so what is the smallest DNS query possible? I kind of answered that question already. This is how it's going to look. 64 bytes, the 512 bytes that are response. Now, a piece of trivia here. The reason there are 13 root DNS servers is because you could only fit 13 in the answer with you could only fit 13 servers in the 512-byte answer. So anyway, so looking at the amplifiers, they pretty much are the same as the reflectors. This is a table that gives you the different quotients of amplification. I have taken this from US CERT. Some of the numbers I don't agree with, but I think it's a fairly good reference. And can give you kind of coarse, like a picture of what can amplify how much. Okay, so DNS reflection, how does this thing work? Well, we have a query type any. We send this query type, and it's going to get all those answers. This is how it's going to look. A lot of data coming back. We're going to have the attacker send a packet, and then they're going to spoof the source IP address. See here, the source IP address is 10.0.0.10, which is the target, and then the reflector itself, which is a recursive DNS server. So this is attack using recursive DNS servers, not the authoritative DNS servers, is going to respond back with the answer. Now, keep in mind that once the first query comes in, this answer is also going to be cached on the recursive server, which means that for every next query, it is going to provide sub-millisecond responses, so it can fire at very rapid, very high rate. So DNS reflection basically is, I do send this bad query, not only very fast to the same server, but I also send it to many servers at the same time. And then the target gets overwhelmed with the traffic coming back. Now, in order to execute this attack, first you're seeing here how I'm using purdue.edu. Well, purdue.edu will never know that anything happened, just because all of those are recursive servers. They do not belong to Purdue or anybody else that's related. And they just cache the answer, and then they send the answer as fast as they can. In some cases, attackers have even registered their own domains because they have control of the content of the actual zone, and then they stuff the zone with a lot of junk just so that they can get better amplification, higher amplification level, because they can stick there as many DNSSEC keys, even though those will be invalid, they're still going to be 4K DNSSEC keys, many of them, and here we have very large answers. So again, I'm just going to reiterate this. Even though you may see a domain here, this in no way can be used as attribution. The reason I'm saying it, because I have seen people go and try to do attribution, which doesn't make any sense. But again, just mentioning it here as a caveat. So any questions on DNS reflected attacks? I'm just going to take a sip of water because my voice is going bad. Okay, I guess no questions. At least I'm not seeing anything. Okay, NTP reflection. So here the situation is similar, but we don't have recursive DNS servers. We have NTP servers. The way NTP works is you have different stratum servers. The lower the number, the closer they are, or the smaller the variance of the answer, or the tolerance of the answer as a matter of time is. So the higher the stratum, the closer they are to either atomic clock or some other way, like radio clocks and so on. And the lower stratum servers basically are what people run on their networks. Now, in some data centers, they may have a stratum 1 server in the data center itself, for example, feeding off a GPS unit that is taking time from the satellites. So this NTP server, an older implementation of it, would store IP addresses in a table. Every time somebody queries the NTP server, it would store the IP address of the client, which is very useful because you know now who is using your NTP server. And if you decide to do maintenance, you know which machines will lose the ability to have time. However, there was one shortcut that they had implemented, that instead of having to log in the server and query the state of the server while you're logged into the machine, there was a remote command that an administrator could issue called monlist, which would basically return a copy of that list to the administrator. Well, you guessed it. What if if a bad guy changes the IP address of the source IP address with the address of the victim? Well, this traffic is going to be sent to the victim. Now, imagine that instead of doing this to one NTP server, they use a very large number of NTP servers, and here the victim is buried with responses. So I'm going to go over this a little bit slower just because I double-clicked by mistake. So the attacker sends a packet, NTP query, monlist query to a NTP server, and then inserts the IP address of the victim in that packet, so the response goes to the victim, and they receive this response. Now, if they do this with a large number of servers, then there'll be a lot of traffic going to that victim. The other thing here is that you can have up to 600 entries that are cached in that lower stratum server. And what we have also observed that attackers do, before they start using a server for reflection, they would prime that cache by sending a lot of queries with spoofed IP addresses, just so that the number of IP addresses here in this table goes all the way up to 600, and then when they start executing the attack, they'll have the full 600 going to the target versus sending, a small packet with 3 entries in it. Questions? Okay. Mitigation strategies. So overall mitigation strategies, there's a number, but the biggest, most important thing, which I already kind of mentioned, is the cost of an outage. Either a minute of outage or a day of outage or an hour of outage, whatever is relevant to the business. This is the most important metric you need in order to start thinking about mitigating DDoS attacks. Unless it is a matter of honor that the website should never go down and somebody has endless amount of money to pour into it, you really need to understand how much money will the business be losing, so that then you can create a case taking into account the risk or the probability of them being affected by the denial of service attack, and then the amount of money that they, or to justify the amount of money that they need to invest into mitigation. So let's see. If we look at the kind of the risk pyramid, this is supposed to be a pyramid, even though it looks like a triangle. If you have at the bottom very primitive basic attackers like script kiddies, booters, and so on, you have a lot of them. So if your bar is low, your defense levels are low, that means that a large number of attackers will be able to go above it and cause denial of service. Then when you put resources into that, into lifting that bar, so you put resources into being prepared to mitigate attacks, this bar is going to go up, which is going to severely limit the number of attackers that can go above that bar and cause a disruption. Theoretically, if you can raise the bar up to the top, there'll be nobody that can take you down. So if this is something that the company is striving for, that's something they should do. If they, for example, can afford to be down 1% of the time, maybe they should not be aiming at 100%. And again, as we know, 100% is very kind of nebulous thing to achieve, because sometimes just simple error can cause an outage. But anyway, so that's the idea there. There are different approaches. So for large companies, it would make sense to do it themselves because they save money because of the scalability, the scale that they have, economy of numbers, helps them save money. Now, if they have to, if the company is smaller, then they can outsource it, and they also can take two strategies. One of them is on demand or always on. And there's always the hybrid that comes from the salespeople, because there were certain companies that would sell hardware, but then they saw that the hardware can no longer really scale up, and they had to come up with a hybrid version where if you go above certain level, then the hardware can no longer help you. Then you send the mitigation to the cloud. We'll go in that in details. So do it yourself, how that would look. Basically, you have the server here that's being protected, or let's say number of servers can be multiple co-locations. I'm just drawing one because it's simpler. And then you have the internet, nowadays known as the cloud. And you have the regular users that are accessing the services of that server, and then you have attackers. Once the attackers start sending traffic, you can enable your mitigation device, and then filter the traffic. Hopefully, it will filter it, and then problem solved. Now, if you start looking here at the expenses, traffic, 10 gigs, about 2K a month. This is from about a couple of years ago. And depending also on how much bandwidth you're buying, this price can severely vary. If you're a large provider, you'll be looking at much smaller numbers. If you're a small company, you'll probably be looking at more than that. Co-location space and so on, power, equipment, and you need also personnel to manage this. So if you're going to do this yourself, you have to have qualified people that understand BGP, understand how to move traffic between locations and so on. And actually, this is the most expensive part here, because here, even at 20K per 10 gigabit port, it's not that much. But when you start adding 6, 7, 8, 10 people managing that network at 200K or more, when you include benefits, then it becomes pretty expensive. Now, conclusions: you have full control, leverages economy of scale. You have a lot of flexibility there, but you really need to have scale in order to be able to execute this or to be able to support this. External services. So those are known as mitigation services, or sometimes advertised as clean pipes and so on. Their pricing is different. Some of them may be based on the attack sizes. Some of them may be based on the nominal clean traffic that is coming to your location. And as I mentioned, the model can be on demand or always on. So on demand will look like this. So you have the same server you're protecting. Here you have either a detection device, or can be also a daemon on the server. Doesn't need to be a separate device. And you have regular traffic. The moment an attack starts, the detection device picks it up, and then it signals the cloud or signals the mitigation provider, which is going to inject a BGP route. And as this BGP route is propagating, it's going to hijack this traffic. So it's no longer going to be coming to you, but it's going to be going to their mitigation pods, which are usually in POPs that are close to large metro areas, and they're basically close to the customers and distributed widely around the network, so they can fragment the attack traffic into smaller pieces. Now, once the traffic gets there, we have a problem because we don't know how to send this traffic back to where the content is. Well, we're going to use a Jerry tunnel, and this is how the traffic is going to get to that server. Now, there is a bit of a problem here, though. If you're looking at, let's say, a frame that is 1500 bytes, DMT is 1500 bytes, and if you're looking at saturated links or like full frames, the moment you insert the Jerry header, each of those will have to be fragmented in two, just so it can go over the Jerry header. So here there's a lot of additional overhead. The overhead is not only the Jerry header itself, but it is the fact that many of those packets will have to actually be fragmented in two and then reassembled later. Then you may add potential loss of packets and then retransmission and so on. So this is not as bad as I make it sound, but it's also not as trivial. So there's a lot of overhead because of the Jerry tunnel. Always on mitigation is another way to go about it. So instead of having the pods inserted when there is an attack, you always have them on, and the actual server is never observed by the internet and consequentially by the attackers. So mitigation provider just basically sits all the time here. The traffic goes to IP space here that nobody knows about. And when the traffic comes in, they do whatever they need to do and they send it back. And they send it back to the server. Now, if you have a content delivery network, there are some added benefits. The content delivery network is going to cache all the static content on those pods. And this is in turn going to accelerate traffic delivery for all of those customers that are not attackers, that are just regular customers. So in my previous job before I started school, that's what we did. We were a content delivery network, and and we were able to cache huge amounts of data. So having in mind that all those pods were deployed in points of presence or POPs that are close to large metro areas, instead of having to go to the servers, let's say, of our customers, which would be maybe 100, 200 milliseconds round trip time, people in Los Angeles will be hitting a local POP with 3 milliseconds to 4 milliseconds worst case round trip time, which would extremely accelerate delivery, because first the three-way handshake happens very fast, then the windows grow very fast because the exchange of packets is instantaneous. Probability of packet loss is also very small, and so on. So this is caching the content, and then when attackers try to attack it, they basically get all the traffic filtered on those pods. And that's it here. The other thing is also that CDNs operate at very high capacity. CDNs usually operate at much higher capacity than the on-demand providers, just because they always run all of the regular traffic on top of them. It's not like they only get inserted when there is an attack. They're always on. There's another benefit also of CDNs, that since they're always on, when an attack occurs, there is no moving parts. It's already there. It's already set up. With the other method here we were looking at earlier, see here, before the signaling happens, I get the attack coming in, then I have to signal, then the BGP route has to be propagated. Usually there'll be a human that may need to interfere after the detection actually and say, yeah, that's legit, do the injection. And this time, maybe 2 to 3 to 5 minutes, maybe sometimes more if somebody has to be paged and look into it. And during this time, there may be degraded service performance or even complete outage until mitigation comes into play. With the CDN or always on, the defense is always on, and thus there is no problem. And here's quick comparison. Okay, sorry, actually, this is the hybrid. I'm clicking way too fast. Yeah, so the hybrid basically will use the two, will combine things. There will be a on-site hardware that's going to mitigate lower level attacks, maybe under 5 gig, under 10 gig, under 20 gig. And then when the traffic starts to go above that level, then it is going to send the mitigation to the cloud. And here's comparison for the mitigation service providers, how it looks. You know, on one side you don't have to deal with the complexity, accelerates content delivery if it's a CDN, and ultimately ends up cheaper than having to do it yourself, unless you're a really large company. Like for example, Google has no point in using an external CDN because Google itself has its own CDN. Same with Facebook. Questions? Okay, that's it.